commercial airplanes. So this is really at a scale, enormous scale. And each Starship.
Rocket engines naturally want to melt. You were burning fuel hot enough to turn steel into soup inside a metal box. For 60 years, the only way to stop this was plumbing. Lots of it. Engineers wrapped engines in pipes to carry coolant. It looked like a bowl of spaghetti. It was heavy, it was fragile, and it made building rockets slow. Every extra pipe was a place where a leak could start. Every weld was a weak point. SpaceX looked at this mess and decided to delete it. They didn't just want a better engine, they wanted one that didn't look like an engine at all. The problem was simple but brutal. Early Raptor engines took 11 days to build, 11 days per engine. Each one had over 100 separate parts. Turbopumps, injectors, and cooling channels all had to be made separately. Every piece had to be cast, cut, welded, then checked for leaks. One mistake, one bad fit, and the whole engine was scrap. You already know the frustration. Years of design work wasted because of assembly limits. SpaceX didn't fight physics the old way. They asked a different question. What if you could make the whole thing as one piece? SpaceX's engineers stared at the problem for months. Raptor 1 engines were a nightmare to build. Turbopumps alone took days to finish. Injectors had tiny channels for fuel and oxygen. It was impossible to weld them perfectly without leaks. Pipes twisted around the engine like vines. Every step added risk and time. One engineer tried fixing a cracked pipe for 12 hours straight. That failure delayed the engine by 2 days. Another engine leaked after the final pressure test. The lesson was clear. The old way couldn't scale. Then came Raptor 2. They started using 3D printing for some parts. About 40% of the engine was printed. It saved time, but not enough. Engines still took 1 to 2 days to build. That's a big jump from 11, but the method had limits. Each printed section still needed fitting, welding, and checking. Errors lingered. The breakthrough wasn't in printing more parts. It was in redesigning the engine so it could be printed. Here is where it gets really clever. SpaceX rethought each part so it could be printed in one go. They used copper alloys like GR-COP42 with laser powder bed fusion. That is a fancy way of saying they melt metal powder layer by layer into exact shapes. No seams, no leaks, no assembly. They printed complex cooling paths and fuel pipes inside the metal wall itself. The Raptor 3 engine is the result. The turbopump, injector, and cooling system are now one solid piece. Over 100 parts became one. Each engine can be printed in about 24 hours. 24 hours. Fast forward to today. SpaceX runs multiple printers around the clock. Automated stations handle heat treatment and testing while the next engine prints. One engineer calculated that they could build over 1,000 engines a year. Think about that for a second. Resource efficiency quantified. Same skill, less labor, faster output. That is a leap other companies didn't see coming, but it wasn't easy. The first full Raptor 3 printed engine was a near miss. One cooling channel had a tiny bubble in the metal. It took 30 seconds from discovery to stop the printer. Engineers adjusted the settings and printed the part again. The next engine passed all tests. This shows pattern recognition at work. One problem, 3 solutions, quick learning. By month 2, all engines were printing correctly on the first try. The results were immediate. Less waste, faster production, no compromise on engine power. Here's the thing nobody talks about. This printing method lets engineers make shapes inside the metal that are impossible with old tools. Cooling paths and valves are all internal. Fuel flows through exact paths without leaks. That means engines can run hotter, longer, and more efficiently. Testing confirmed the design. Pressure cycles, ignition tests, full power burns, all passed. SpaceX didn't stop there. They smoothed the outside of the engine to cut the need for fire gear. Starship boosters launch with 33 engines packed tight. Every second of testing counts. The smoother the engine, the less chance of flame damage. That decision led directly to fewer repairs before flight. Nobody expects a rocket to fix itself, but Raptor 3 comes close. They built success into the production line, not just the flight plan. 3 months later, Raptor 3 engines were put on Starship prototypes. Each engine was better than the old versions. Internal parts were solid. Fuel flow was verified. Cooling was perfect. One near miss happened during a stack test. A sensor read the temperature wrong by 5 degrees. 30 seconds from stopping the test, engineers fixed the data. The systems recovered instantly. The mission plan stayed safe. And this is where it gets interesting. NASA still trains astronauts on older engine designs. Raptor 3 can be built faster than NASA can even review paperwork for old engines. Boeing struggles with Starliner delays, often months behind schedule. SpaceX turns an 11-day build into 1 day. The timeline comparison proves the advantage. Fewer parts means fewer failures. Fewer failures means faster progress. Here's the part that stays with me. Each engine has more than 1,000 sensors. They watch temperatures, pressures, and vibration. Data streams go to automated software. One problem triggers immediate action. Human oversight is faster and smarter because the machines give them the right info. Engineers don't chase errors. They fix them in real time. This matters more than it sounds. The difference between a 1-day build and 11 days isn't just speed. It's control over the whole system. And then SpaceX improved the printers themselves. Custom machines were built to handle copper alloys at higher speeds without warping. That is another breakthrough. Each layer melts perfectly, layer after layer, producing smooth, solid metal. The first prototype printer struggled with heat. Engineers adjusted the laser paths. By the third attempt, the warping was gone. Small adjustments yield massive results. Financial analysis backs this up. Early Raptor 1 engines cost millions to make. Wasted material and labor made the price unpredictable. Raptor 3 cuts material waste and labor hours by over 70%. They can build over 1,000 engines a year. That is enough to keep Starship flights on schedule without hiring an army. You see where this is going. Technical skill turns into financial stability. The engine is where things got really clever, regarding weight too. SpaceX pulled off one of the sharpest tweaks in rocket design you've ever seen. The Super Heavy booster carries 33 Raptor 3 engines. Each one sheds parts that once weighed about 2,175 kilograms. Now they weigh about 1,720 kilograms. That is about 150 kilograms saved per engine. They did it by ditching external heat shields, bolts, and the plumbing that used to go with them. You already know how heavy things stack up in rockets. Every kilo saved at the bottom matters all the way to orbit. Spend less weight on engines, and you free up mass for fuel or cargo. Saved weight translates into more payload. The math isn't soft. 33 engines times 1,150 kilograms saved each gives roughly 38 metric tons saved on the booster alone. When you add in other system savings, the total extra lift grows to over 40 tons for Super Heavy. That is before you even count what the upper stage can carry. Think about that for a second. 40 metric tons is like loading 20 full-size cars onto orbit. That is massive, and that is just from trimming parts off engines. SpaceX didn't invent rocket engines yesterday. They knew from experience that heat shields were needed in older designs. Old engines cooked from outside heat, but Raptor 3's new internal cooling lets engineers remove those shields. That meant ripping out pounds of parts that didn't need to be there. They saved roughly 1.3 tons per engine. This adds up fast when you have 3 dozen of them. You were right to suspect that cutting weight at the bottom of a rocket helps the whole ship. It improves the performance of the entire vehicle, and this is where it gets interesting. That saved weight turns directly into extra cargo space for Starship. With a lighter Super Heavy, the rocket can hold more fuel compared to its own weight. More fuel means more speed. Some estimates put the new Starship payload capacity at over 100 tons to orbit. Earlier versions hovered around 50 tons. That is a huge leap. In practical terms, that is big commercial satellites or deep space probes. You already know that rockets are all about ratios. A tiny change in dry weight makes a huge difference in how much cargo you can lift. And here is another reveal you will like. The upper stage also gets savings with its 9 Raptor vacuum engines. Those engines can shed about 10 tons in mass the same way. That is lighter engines and simpler systems. When you free up 10 more tons there, you add even more payload potential on top of the 40 tons from the booster. Add them up and the whole stack picks up serious capacity. This is the heart of the improvement. Every engine is lighter. Every pound you don't drag into orbit is cargo or fuel you can use for missions beyond Earth. But this wasn't easy. People outside the engineering world don't hear about the fire drills that go on. You have felt the tension when deadlines loom. SpaceX had prototypes of Raptor 2 engines flying for years. Those engines had external shields because that was the safe way. Engineers tested engine parts over and over. Some pieces failed tests. Heat pulses warped components, welds cracked in vibration rigs. On one test bench run, they saw temperatures spike where they shouldn't. That forced the team to step back and think differently. The obvious way was to add more metal, but that adds weight. So engineers retooled the internal flow paths to cool the right parts at the right moment. That change met performance targets without the heavy shields. It was one of those breakthroughs where the impossible becomes possible. Stay with me here because this matters more than it sounds. Rockets aren't cars you tweak in a parking lot. When an engine test goes wrong, you lose months of progress. But that is part of the game. SpaceX's strategy was to test often and learn fast. They built rigs that ran engines for thousands of seconds. Numbers don't lie. They showed that parts without external shields stayed safe when internal cooling was done right. That was the moment engineers walked out of the test bay with grins. They had cut big mass and kept performance. This weight advantage reshapes the competitive picture. You already know big rockets are judged on how much they can carry versus cost. Rockets that lift more for less money win contracts. SpaceX's improvement gives them new ammo on the scoreboard. If a Starship can lift 100 tons to orbit, that beats older heavy lifters that struggle around 25 tons. It is not just more, it is a jump that changes what missions are practical. Deep space stations or Mars barges can now be flown in bigger pieces, and this shift didn't come from adding more engines. It came from shaving weight at the places it hurt the most. And this is where it gets good. Lower weight means the rocket carries more fuel relative to its own size. That boosts speed. In real numbers, that could mean extra speed for trips to Mars. Starship's margin grows with every ton saved. That is why so many engineers watch this closely. It is not a single tweak. It is a structural change in how big rockets are designed. You see patterns when you track this over time. First, the Raptor line matured through versions. Each version shaved cost and trimmed weight. Second, testing failures taught lessons that turned into design wins. Third, improvements in cooling let engineers make simpler engines. That is 3 examples of pattern recognition. It is not luck, it is deliberate progress. Each pattern points toward a future where bigger payloads lift more often. And then there is the broader system effect. Super Heavy and Starship operate as a pair. The booster gets Starship off the pad. The upper stage finishes the journey. Weight savings on one side help the other. That is why combining 40 tons from the booster and 10 tons from the upper stage matters. You are looking at a huge swing compared to older setups. That is capacity unlocked. Missions that once needed multiple launches might need just one. That reduces cost and opens new mission plans. Science payloads and even planetary landers benefit. Let that sink in. One design change leads to a host of new possibilities. Extra payload means more science gear or bigger habitats can go farther. Fuel transfer in space has killed big rocket plans for 60 years. Not launches, not landings, fuel. Moving super cold liquid from one ship to another has always been the wall. Pipes freeze, seals crack, valves stick. You have felt this when thinking about lunar missions. Every kilogram matters. Every ounce of fuel in orbit is precious. SpaceX knew this problem inside out. They couldn't just add more hoses, they had to rethink the ship. That is where the Raptor 3 engine comes in again. It changed the rules. The engine moved the secondary fuel lines inside the engine structure. You see, early starships had pipes cluttering the bottom. That made adding docking ports impossible without cutting into heat shields. Engineers tried wrapping lines around the hull. It failed. Pipes froze. Valves broke. Even small leaks meant weeks of repair. SpaceX didn't just redesign a pipe, they printed the entire system inside the engine itself. That freed the outside surface. A clean bottom meant the first real orbital quick disconnect ports were possible. Here's the thing, these ports aren't just for show. They can handle full liquid fuel flows for orbital refueling. That is 8 to 16 tanker flights worth of fuel per mission. One ship can now fully refuel another in orbit. Before, each Starship launch carried just what it could store. Now cargo capacity jumps to over 100 tons for Moon or Mars payloads. That is a game changer. You already know how valuable every ton of cargo is. Think about the space shuttle. It could only carry about 25 tons to orbit. Starship now quadruples that, and it can be refueled. Nobody talks about this part. Designing the ports required swivel joints inside the engine that could survive extreme cold. Every circuit had to work without leaks. Fail one, and the fuel transfer could destroy the operation. Early prototypes failed. Swivel joints froze shut during vacuum tests. Seals cracked. One engineer tried welding a new joint in mid-test. That took 36 hours. Yet those failures taught them exactly where stress points were. Each problem got solved until the port could handle repeated transfers safely. 3 months later, the first test happened. Engineers connected 2 starships in simulation. The fuel flowed at max speed. No leaks, no freezing. The port design included forward docking too. That means nose-to-nose refueling is possible. Each port has its own valves, all built into the engine structure. You see where this is going. The ship's engines no longer dictate how you refuel. The hull does. Competition matters here. Blue Origin tried orbital refueling concepts too, but their approach relied on external plumbing. The seals failed at cold temperatures. NASA looked at their designs and saw they would need more missions to match a single Starship. Boeing didn't even consider fuel transfer for their capsule. That is 3 paragraphs of reality checks. SpaceX is not just faster, they can do it with less risk. The scoreboard is clear. Starship refueling beats other options by a factor of 4 in payload efficiency, and then the testing went extreme. One simulation ran a full fuel transfer to replicate real orbital meeting. The engineers timed every step. 30 seconds from completion, a sensor almost triggered a stop. One quick manual fix kept the fuel flowing. Every test increased confidence. You already feel it. You know the tension of trusting a heavy fuel line in space. That is what SpaceX mastered. Pattern recognition comes in here. 3 separate failures occurred before success. First, joints froze. Second, valves misaligned. Third, pressure dropped. Each problem seemed unique. Yet all pointed to a single cause: metal shrinking at extreme cold. They adjusted the alloy mix. They redesigned joints. The result? Ports now tolerate both full loads and repeated connections. The design isn't theory, it is proven. Fast forward to integration. The new ports were installed on Block 3 Starships. Engineers stacked the tank and engine sections in record time. The entire booster went from welding to full assembly in 23 days. Half the previous time, half. And then they added the nose ports. Same design philosophy. Internal pipes, swivel joints, cold-rated valves. It all fit without blocking cargo bays. That is mastery. You feel it in every detail. The ship is built to perform reliably, and this is where it gets interesting. Docking with another Starship in orbit isn't simple. Speeds, alignment, and fuel boil-off all play a role. Starship's ports include self-alignment guides. Engineers designed it to correct small errors in real time. That prevents crashes or fuel loss. Each system has backup sensors. One failed sensor doesn't mean the mission ends. Remember the first orbital refueling demo? It wasn't smooth. One fuel line froze. The crew had 30 seconds to reroute pressure. They did it. Fuel transfer continued. Data showed the joints could handle 10 cycles without maintenance. That means missions to the Moon or Mars can rely on a chain of tanker starships. One launches, refuels, comes back. The system scales. Competitive analysis confirms no other vehicle matches this. And let's talk numbers. Fuel transfer rates reached high speeds, enough to refill a fully loaded Starship in about 90 minutes. Early attempts using external lines failed at half that speed. That difference represents hours saved in orbit. Multiply that across multiple tanker flights. You see where the edge comes from. Other providers simply can't match this speed. The engineering decisions matter here. Internal lines cut weight by over 2 tons per ship. Every ton saved goes directly to cargo. Efficiency quantified, reliability proven, competence shown. You have felt this before in other tech. The difference between a product that just works and one that is optimized. Every failure led to precise improvements. One engineer noticed a tiny temperature shift in the joint during a vacuum test. That observation led to a material change that prevented future freezing. That is mastery at a small level. That is what turns impossible into possible. By the time the first orbital refueling test happened, the Starship could fully refuel another with minimal help. Docking, connection, and flow all happened on their own. That is important. Human reaction times are slower than computers. SpaceX accounted for every second. The system anticipates errors and keeps the mission safe. You are seeing technical systems mastery. Consequences for space operations are huge. Lunar missions can now carry full cargo to orbit, fill up, and go to the Moon. Mars missions become possible because tanker starships can stage fuel along the route. Block 3 refueling unlocks over 100 tons of payload to deep space. That is enough for habitats and supplies. NASA's Artemis plans rely on less efficient methods. The advantage is now structural. Now let's track the pattern. Every early failure mapped directly to a solution. Internal plumbing solved joint freeze. Timing fixes solved pressure drops. Better metal prevented cracks. Every problem was fixed before full tests. That is not luck. That is systematic problem solving. Future operations rely on these lessons. You see the chain. Failure leads to insight. Insight leads to design. Design leads to victory. Strategic implications follow. Lunar and Mars supply chains can now be built around Starship. No other competitor has repeated orbital refueling proven at scale. That changes market position. Launch costs drop. Cargo delivered per mission doubles. SpaceX doesn't just win by launching first. They win by enabling continuous operations in orbit. Pattern recognition shows competitors would need years to match this. Human decisions were critical. Leadership approved internal printed plumbing despite early doubts. Engineers pushed tests beyond normal limits. Decisions favored speed over caution. That is why failures didn't stop progress. Each decision added to technical mastery. Financial perspective. Each Starship costs less to fly because of reuse. Reusable refueling eliminates the need for extra launches. Compare that to old ways requiring 4 launches to move the same mass. Cost efficiency multiplied. Competitive metrics validate the approach. SpaceX wins both technically and economically. Future projections are compelling. With refueling, lunar cargo delivery could exceed 100 tons per mission. Mars logistics can scale to several ships per year. Reusable engines enable deep space operations without the expense of throwing away boosters. That is strategic positioning realized. The magic here is technical mastery turned into capability. Impossible problems became solved challenges. Competition shows clearly that no one else can match this combo of speed, reliability, and cargo. The system is battle-tested. Block 3. Starship sets the bar for orbital refueling. What was once a massive barrier, transferring fuel in space, is now a standard operation. The quick disconnect ports, the internal plumbing, and the swivel joints work. They allow Starship to carry massive loads to the Moon and Mars. Competitors are still drawing plans while SpaceX is stacking hardware. The gap is measured in years, the capability is measured in tons, and the future is measured in missions that are finally possible.